Hello! In this video I'm going to show you how to calculate lengths and angles in three-dimensional shapes. But in order to do that, you need to be very good at two-dimensional trigonometry. You should know how to use the sine, cosine and tangent ratios to find angles and the lengths of sides in right-angled triangles. You also need to apply Pythagoras' theorem. So, if you have those skills, you can watch the examples that I'll show you in this video and then have a go at the online exercise. The address is down here. There are 5 levels of difficulty, and if you complete a level, you'll earn a virtual trophy. Now, most of the questions are about common mathematical solids like cuboids, prisms, pyramids, and this one is a tetrahedron. A typical question might be something like, find the distance between the opposite vertices, that's corners, of this cuboid. Well, it's sort of the frame of a cuboid. I have to show you what's inside because that's the line that we need to measure. If I get my tape measure here and put one end at that corner, then stretch the other end down to this corner, that is the length of the diagonal of this cuboid. It's the distance between opposite vertices, and that's typically something you may be asked to calculate. Now, here's a spoiler. The basic technique of answering all of these questions is to try and find two-dimensional right-angled triangles in the three-dimensional shape and make a little sketch of those two-dimensional right-angled triangles, and then you can apply your trigonometry or Pythagoras to find the answers. Okay, let's begin with a story. In days of old, when knights were bold, and dragons still breathed fire, there lived a knight, a clever knight, Sir Pythagore Esquire. He had a lance, a sturdy lance, it measured 13 feet. He had it with him just in case a dragon he should meet. But when he came to cross a bridge, the guards they did implore, the longest thing allowed across is 9 feet and no more. Sir Pythag puzzled long and hard, this problem was a quest, until he found a carpenter to make a wooden chest. The chest was made in record time, not long did Pythag wait. The chest could cross the bridge because 'twas 8 by 8 by 8. Now if you do the maths you'll see, the diagonal is a line of length worked out with 3D trig, roughly 13.9. That's big enough to hold the lance, with room to spare of course, but such a chest and the knight are too much for his horse. So, with that in mind, let's see how they used maths to calculate the length of that diagonal. So this is what the chest would look like if you drew it as a line diagram so that we can sort of see through this three-dimensional object, even though it's given here on a two-dimensional screen. So each of the dimensions are 8 feet. And what we have to do is work out how far is it from one corner to the very opposite corner down there. Now, we don't know how to do trigonometry in 3 dimensions, so let's look in the diagram and see if we can find a two-dimensional right-angled triangle. I'm going to label the sides, the vertices, so that we can talk about them. And there can you see DHF? That is, well, in this case it's sort of a perspective drawing of a right-angled triangle, which if I drew it just in 2 dimensions would look like that, with a right angle down at H, and we know that the height DH is 8 feet. The trouble is we don't know how long HF is, we don't know any of the angles, but that red line, the diagonal, is the hypotenuse of that triangle. So let's go back to our three-dimensional diagram of the cube, and let's see how we could figure out what HF is. Well, I think we could draw a green right angle triangle there, shown in perspective, so that you have to imagine this, if you're looking from the top of the cube, looking down on the base, then that would look like a right angle triangle. So let me sketch it out there. Now we know that that has got two shorter sides, each of length 8 feet, so we can use Pythagoras' theorem to work out HF. Now we know HF. I've written it down there. I've given it to 5 significant figures, and I've put an ellipses ... at the end of it, but I'm actually keeping the full value on my calculator, not doing any rounding at this stage. I can now put that value as that side HF of my yellow, my first right angle triangle. And now I can use Pythagoras' theorem on those values to work out the length of the hypotenuse, which turns out to be 13.86 feet to 2 decimal places. Right, well that's easily long enough for Pythagoras to put his lance in this box, because it's longer than 13, that diagonal, but the box itself doesn't have any dimensions longer than 8 feet, so it would be allowed to cross the bridge. Amazing. Okay then, so we're preparing now to do level 1 of the online exercise. You can see the address there. And let's have an example first using a cuboid. So this is a very typical sort of question you might get at this level. Here is a cuboid, and I can see that the dimensions are given as 20 centimeters, 4 centimeters, and 5 centimeters. I'll put letters on each of the vertices so that I can refer to them. And I'm going to draw in as best I can with that yellow line the diagonal from one corner to the opposite corner within that cuboid. Okay, just as before, we draw a two-dimensional right angle triangle that contains the length that we're trying to find. So in this case, I've drawn the triangle EHC, and I've let X be that distance that we're trying to work out. So I know that EH is 4 centimeters, but I don't yet know the length of CH. That's the diagonal of the base of that cuboid. But just as before, we can draw another right angle triangle. This is the one that you see when you're looking down on at the base of the cuboid from the top. Can you see the letters H, G, and C help you see where it fits into the three-dimensional diagram? And there we do know the two dimensions are 5 and 20, so using Pythagoras we could work out HC, or CH, as I've written down here. Use that full value, that answer, to go back to the first right angle triangle that I drew, and now we can use that to work out what X is, again using Pythagoras' theorem. So we've used Pythagoras' theorem twice. And because I've done a lot of questions like this involving cubes and cuboids, I've noticed that actually we could have answered this question using sort of a three-dimensional version of Pythagoras' theorem. You see that X, which is the length we're trying to find, the diagonal, is actually the square root of those 3 dimensions each squared. So I can put the values in, the 20, the 4, and the 5, and then do the calculation and get X is 21 centimeters, and that is the length of the diagonal from corner to opposite corner, or vertex to opposite vertex of that cuboid. I think now you're ready to do level 1 of the online exercise. Go and have a go. Keep clicking the check button to see if you're getting the answers right, and then come back here for level 2. Right, let's go into level 2 now with this shape, a triangular prism, and each of the triangular ends of this prism are right-angled triangles, and we're given some information about this prism, and I've shown this now on the diagram, the lengths and those two right angles there. So we're sort of looking inside the prism here. Okay, we have to work out the angle between AF and DF. So just as before, we look to find a right angle triangle that contains this angle. And there it is, triangle ADF. So if you look at the three-dimensional diagram and see if you can visualize that, and we need to work out that acute angle at F. So we know AD, the height, but we don't know DF. So just as before, we have a look at another right angle triangle in the base of this prism, and that enables us to use Pythagoras' theorem with the 35 and the 14 centimeters, which of course is 140 millimeters, and I've put that in the calculation using standard trig, that the angle then is the inverse tan of 29 over the square root of 35 squared plus 140 squared, which turns out to be 11.4 degrees, correct to three significant figures. And yes, I was expecting a very small acute angle, so that angle does seem right. Oh, if we go back to that wooden box, that chest that was made for Pythagoras' lance, we could also use this to calculate an angle. Let's put our yellow triangle back in that we had before, and let's just use standard trig then to work out the angle that the diagonal makes with the base. It's that angle DFH. So again, using tan, the angle works out to be 35.3 degrees, which, even though the diagram is not drawn to scale, does seem to be reasonable for that sort of angle. Okay, so now have a go at level 2 of the online exercise, and then come back here when you're ready for level 3. So level 3 now is going to involve a square-based pyramid. And the sides of the square base are each 28 meters, and the angle that the sloping edges make with the base is 65 degrees. We need to work out the height. That's the perpendicular height, or the vertical height, of this pyramid. So I'm going to, well, I won't label all of the vertices this time, just the ones that will help us. I'll label the top A and that corner B, and then, well, you can't see this point, it's the center of the square base of the pyramid, so it's sort of underneath there, and that will be point C. But that will enable me to draw a right angle triangle, A, B and C, where AC is the height that I'm trying to find. Now CB, from the center of the square base to the point B, I don't know that length, but just as with the other questions that we've done, we can use Pythagoras, and this time it's half the length of the sides of this square base that form the shorter side of this red right angle triangle. So I'm sure you can see that CB will work out to be the square root of 14 squared plus 14 squared, where 14 is half of that 28. I'm going to leave it in that format and put it in the equation using the tan ratio from my first right angle triangle, so the whole thing can go into the calculator in one go, and I can work out that AC is 42.5 meters to 3 significant figures. Yep, that seems a reasonable answer. I'm happy with that. Now the questions in level 4 don't have diagrams. You have to draw your own. So let's have an example of the sort of question you might get in level 4. A 12-meter flagpole is situated at one corner of a 22-meter by 42-meter rectangular field. What is the angle of elevation of the top of the flagpole as seen from the opposite corner of the field? So I'll sketch my flagpole here, and again it doesn't have to be that beautiful. I'll sketch a perspective view of that field. I'll put some measurements on there so you can see where the longer side of the field is and where the shorter side is. And then I'll imagine this right angle triangle, which is shown here in perspective, and it's the acute angle at the furthest corner of the field away from the flagpole. That is the angle of elevation that we require. So let me draw that right angle triangle, not in perspective but in 2 dimensions. And I can see that the height of the flagpole is 12, so I'll put that in. And again we're going to use that trick of using Pythagoras' theorem on the 2 sides of the base to find the length of the base of this right angle triangle. I haven't worked that out yet. I'm going to keep it in that square root format in my calculation that I'm going to use to work out this angle of elevation. Let's call it theta. So the tan of this angle, theta, is the opposite over adjacent. So using the calculator, I'll work out then that theta is equal to 14.2. That's the angle of elevation to 1 decimal place. Have a go at the questions in level 4. Don't forget to draw your own diagram to help you work out the answer. Now we're on level 5 of the online exercise, where we have to find the angle between 2 faces. So in this case it's between face ACD of this pyramid. It's a rectangular based pyramid with a height of 7 centimeters, and the angle between that face and the base BCDE. Right, so rather than finding the angle between faces, I'm going to draw lines on the faces that are perpendicular to the edge along which the 2 faces meet. And that's the angle within that triangle that we would find, which is equivalent to the angle between the 2 faces. So I've drawn my right angle triangle just as with all the other questions here. Put on the information that I know. Of course 3.1 is half of that 6.2. And now it's easy to calculate the angle G using the tan ratio, the tangent ratio. It's 66.1 degrees to 1 decimal place. Okay, now it's your turn to have a go at the online exercise. Don't forget to press the check button regularly as you're working through the questions to see if you're getting them right. And if you make a mistake, have another think and correct your answer and then press that check button again. Don't forget to claim your trophy when you've got to the end. And there are lots more activities on the Transom website for you to have a go at to improve your mathematics, and you can claim hundreds of trophies. So, what are you waiting for? Get going! Bye!
You can find Transom Mathematics at www.transom.org, where you're welcome to use all of the activities absolutely free, or jump in with both feet and become a Transom subscriber.